Hey, hi everyone. So in the previous video, we already talked about that if there are two factors affecting capacitance. So previously we talked about the dimension of capacitor, where the area of the capacitor plate in the distance will affect the capacitance through this equation over here. The next factor is the presence of dielectric. So if you happen to insert a dielectric, what happens is it will affect the permittivity of the space in between the capacitor plate. So affect by how much can be decided by this value, which is the relative permittivity, which acts like a multiple, okay, to multiply to the original permittivity, which is permittivity of free space, to obtain the permittivity of the space right now, which is filled by the dielectric, the permittivity of dielectric. So we know that this insertion of dielectric always increase the permittivity, therefore it always increase the capacitance. So relating to that, I'm going to continue with it a bit. So the idea is we know that the insertion of dielectric always causes the the capacitance to increase, right? So we know that if we go from this C naught to this C over here, this is a C naught without the dielectric, this is a C with the dielectric. We know that going from C naught to C is always an increase. Okay, why is it always an increase? It's because epsilon r is always greater than 1. Okay, epsilon r again is the relative permittivity, and because relative permittivity is always that's bad handwriting, it's always greater than 1, so it will only cause the value of permittivity and the value of capacitance to increase. Okay, so we know that going from C naught to C will cause the capacitance to increase. Okay, so now we write down, we know that this is the original C, which is called C naught. This is the after insertion of dielectric, the new C is without the naught. So naught usually carry the idea of initial, right? So initial, if there's no dielectric, that's why it's C naught, not C default, okay, C original, okay. So once you insert a dielectric, it becomes a new version, so that's why there's no longer a naught over there. Okay, so we know this is C and C naught, so we know that C is definitely greater than C naught. But now I would like to recall something that you have learned in the previous video. You know that capacitance, if you refer back to its definition, is the ratio of charge stored to the potential difference across the plate. So you know that the capacitor is a stored charge, so there's a value of Q over here. Then it's why is there a charge being stored? Is because you connect it to some kind of power supply to bring charges from one plate to another plate. So the presence of charge being stored in the plates will cause a potential difference to be set across the plate. So the one that is storing positive charge will be a positive plate. This one that's storing negative charge will be a negative plate, and positive plate will be having higher potential. Then the negative plate will have lower potential. So this is what we label as V high and V low, and then because of that, there's a potential difference. This is what we have discussed already. So bringing that to this particular topic over here, we know that the same idea over here is the same idea. There will be charge being stored, positive Q, negative Q, and resulting in one plate to become V high and another plate to become V low. So therefore, in between them, there's a potential difference V. Okay, we are not using delta V anymore. Delta V potential difference is only for chapter 1. Moving on from chapter 1, potential difference is now being called as V. Okay, just want to save some ink. Okay, so this is positive charge Q, negative charge Q. Then, of course, because of that, you have V high, you have V low. Okay, and because of that, for sure you have V, a potential difference. Okay, so but we need to know that the capacitance already increased. So we know that C is equals to QV, okay? This is Q over V. This is what we have known from earlier, from the previous video. C is the ratio of charge stored to the potential difference across the plate. So if we know the C has increased, if we know that the C has increased, so what will happen to the Q? Does it mean by it increase? And what will happen to the voltage? Does it mean by it will decrease? Okay, is that what happened? Well, there's a bit of things that you need to explain in order to understand this. Okay, but before we go through to really figure out whether it's the charge that is increasing or the voltage that is decreasing in order to match the increasing capacitance, we should actually try to define some symbol first. We are not supposed to say that this Q increase then become the same Q. This V decrease become the same V. We should not be using the same symbol for something that has changed, okay? So Q here should represent the charge stop when there is no dielectric. Q here should represent the charge stop when there is a dielectric. So we should be able to differentiate them by having different symbol. So by keeping consistent with the idea of having not over here for without dielectric, we are going to use the same idea by giving a not for without dielectric. So Q naught over here represent without dielectric, V naught over here represent without dielectric. So we are going to edit the diagram a little bit. This one will be called positive Q naught, negative Q naught. This one is called V naught. Okay, I hope you don't get it confused with another knot that you have seen earlier. Last time when we are talking about this, okay, when we are talking about this, there's a Q naught over here. This is a different kind of knot. This is like maximum Q or maximum V. That one is another knot. That one it will be discussed further in section 3. Okay, but this Q naught over here, it's referring to without dielectric, the charge stop without dielectric, the potential difference across the plate without dielectric. Whereas if there's no knot over here, is with dielectric, the charge stop with dielectric, and the potential difference across the plates with dielectric. It's just a difference in whether there's dielectric or not. Then you label one with not for without dielectric. Without not is with dielectric. Okay, I hope it's not confusing. Okay, with dielectric there's no not. Without dielectric there is not. Okay, so in order to understand whether it's a Q or the V that will be changing to match with the increasing capacitance, we need to consider two different scenarios actually. Okay, so I'm going to show you the two different scenarios in order for us to discuss it a little. Okay. Okay, so scenario 1 is if the charge capacitor is connected to power supply. Okay, in this case, battery or any kind of DC power supply will be fine. Okay, so scenario 2, on the other hand, will be a charge capacitor not connected to power supply. Okay, so to illustrate the situation, I'll be drawing a capacitor. Okay, so this capacitor here, it's connected to a battery. Okay. Okay, we ignore the resistor for now because resistor is only important in the third section. Okay, so this one is not connected to the battery, not connected to a power supply. So I'll assume that it's not connected to anything. So I'll just leave that space blank to indicate that it's not connected to anything. Okay, not connected to anything. Okay, so what do we know about a battery? So battery, the function of battery is to act as like a charge pump. Okay. Remember, battery is like a pump. Okay, so if battery is like a pump, what happens is if you insert a dielectric inside the space right now, maybe I should draw in another diagram. Okay, insert a dielectric into it. Probably should work on my drawing before I record my video. Then my video will be shorter. Okay, right now I'm inserting a dielectric into it. Okay, so what's the effect of this? We know that the capacitance has increased. It goes from C naught without dielectric, right? So this is C naught is equals to Q naught over V naught. It goes to become C is equals to Q over V. Okay, the battery acts as a pump. So if the battery acts as a pump and the pump is still there, so means by charge can still be pumped from one plate to another plate. In this case, it will be pumped from the lower plate to the upper plate. Okay, so before this it was Q naught positive, then now it's become Q positive. This one on the other hand is negative Q naught. Right now it become negative Q. Okay, so it can continue to pump charges from the lower plate, the positive charges from the lower plate to the positive plate. It is possible because the presence of battery over here, so it can still pump charges. So if it still can pump charges, that means by the Q has a possibility that it can change. Can change. Why can it change? Because there's battery. Okay, but now let's talk about the voltage. We know that a battery, right? A battery has a fixed voltage. Okay, if you buy a typical battery, you label their voltage. For example, let's say here I have a battery. Okay, this is a battery, a D size battery, I think. Is it? Can't remember. Okay, for this particular battery, you can see the label over here says that it's 9 volt. I'm not sure whether you can see or not, but every single battery, they have their own voltage. Okay, so that voltage itself is fixed. So if the voltage itself is fixed, means by if I insert a dielectric into the capacitor, it will not affect the voltage of my battery. My voltage of battery will remain as 9 volt, like for if I use this battery that is mentioned earlier. Okay, if I use another AA battery, then it might be 1.5 volt, but the battery voltage never change. So if the battery voltage never change, then what happens is the voltage of the capacitor will have to continue to obey the same voltage as earlier, because the battery is not unplugged yet, right? The battery is still connected to the capacitor. So if the battery is 1.5 volt, then the capacitor right now is 1.5 volt. No matter if you insert a dielectric into it, because it is still connected to this power supply, you still have to obey the same voltage, which is 1.5 volt. So that's why the voltage over here cannot change, because it's still connected to the power supply. Okay. There's actually a lot more explanation behind why it cannot change, of course. Okay, basically, to lightly glance through the idea, we know that a battery, right, when we say it's 1.5 volt, that means by the positive terminal over here is V high, the negative terminal here is V low, and the difference in the electric potential or the potential difference between V high and V low is 1.5 volt. That's the ideal 1.5 volt battery. Okay, so if this one is, let's say, 0 volt electric potential, then this one will be 1.5 volt electric potential. So if this is 1.5 volt, then it means by this upper plate here, we have to have 1.5 volt. If this is 0, then this one should be 0 volt. You have to make everything connected to it to have the same electric potential. Okay, so if this is 1.5, then this will be 0. So 1.5 minus 0, you still get 1.5. That's why the potential difference cannot change, because you're still connected to the same power supply. So if Q can change, but V cannot change, then what happens is we can get a conclusion that V is constant. Okay, I should write V is constant. So V is constant means by V will be V naught will be equals to V. Okay, no changes. Okay, so knowing the idea that C is equals to QV, and the fact that C to C is C naught to C is an increase. Okay, how should I write it? I should just write C increases lah. Okay, that will make more sense. Okay, and C increases. So if I tell you that my C is increasing, my C has increased, okay, but my V remain constant. So to make the mathematics balance out, C increase, V constant means by Q must definitely increase. Only by increasing the numerator, the answer can be increased. So if we know the answer is increased, the numerator has to increase, provided the fact that the denominator is constant. We know the denominator is constant based on what we discussed earlier. So you know what can only happen is that the numerator or the charge stored will increase. Okay, so Q increases. So we know that if this is Q naught, this is Q, we know that it has progress to be greater. Okay. Okay, so this is the idea right now. So now we move on to the second scenario. Okay, moving on to the second scenario, charge capacitor not connected to the power supply. So not connected to the power supply, what happens if we insert a dielectric right now? Okay, if we do not connect it to a power supply and we insert a dielectric inside it, okay, it should fill all the space in between. You should not leave any empty gaps over here. Okay, but this is just illustration, right? So right now you're inserting a dielectric inside it. So now let's try to study what will change, what will not change. Again, we'll write down this one is C naught without dielectric, Q naught charge stored without dielectric, V naught potential difference without dielectric. Now with dielectric, it becomes C over QV. Okay, we know for sure that C increases. This is what we have known. Okay, C has always increased. Okay, so we know that, let's try to discuss about Q maybe. Okay, if you want charge stored to change, okay, remember the charge store initially is positive Q naught. It over here, now it become positive Q, whereas here it's initially negative Q naught. Then now it becomes negative Q. Okay, so if we want the charge Q naught here to change to become Q, let's say you want it to increase or you want it to decrease, what should happen is you need charges to move from one plate, shift it to another plate. Okay, if you want more charge to be stored, you bring more positive charge to the upper plate, then the Q naught will become, you increase the negative Q naught will become more negative. Okay, if you want to decrease the charge stored, then what happens is you just bring some positive charge back to the lower plate. You bring some positive charge back to the lower plate, and the amount of positive charge stored in the upper plate will decrease. The amount of negative charge stored in the lower plate will decrease as well. So this is how you change the charge stored in the capacitor, by bringing charges from one plate to another, either one direction or the other, to increase or decrease it. But the problem that we have right now is there's no battery connected to it. So if there's no battery connected to it, technically you lost your pump. There's no pump anymore. So if there's no pump anymore, you cannot bring charges from the negative plate to the positive plate anymore. You cannot bring it up to the positive plate anymore because the pump is just not there. It's like if you have some water on the ground, you want to shift it into the water tank up there. Without a pump, you cannot make it work. Okay, of course, there's many other ways, of course, but let's say the only thing you can use is a pump. If there's no pump, you cannot pump it to the higher place. It's because, yeah, it's reverse how natural things flow. Okay, so it cannot be done without a pump. But if you want it to flow down from the, if you want charges to come out from the positive plate, go back to the negative plate, that is very much possible actually, because naturally things will want to fall. We know that positive plate over here, high potential, negative plate over here, low potential. Naturally, positive charge will want to go from positive plate to negative plate because it goes from high potential to low potential. Just like if you let go of a ball, it will naturally fall from high to low. But in this case, it cannot happen as well. Why can't it happen is also because you're not connecting it to anything. Okay, there's an empty gap over here. Okay, if there's an empty gap over here, there's no complete path for the charge to flow. If you use a wire and connect this gap over here, if you use a wire to connect this gap over here, then it's a different story. Now it's entering discharging. You lose all its charges. Okay, but right now I'm not connecting to power supply. I'm not connecting it to anything. When I'm not connecting it to anything, there's a gap over there where charges cannot flow through. So the circuit is not connected. Okay, there's no path for the charges to move. That's why your Q over here will be reserved. Nothing will change to the charge stored over here because the charge cannot flow at all. Okay, so Q over here cannot change. Okay, cannot change. Why does it cannot change? It's because no path for charge to flow. Okay, now how about the voltage? How about the potential difference? Can the potential difference change or not? Well, just now in the first scenario, we say that the voltage cannot change. Why does it cannot change? It's because there's a battery there, right? So if the battery sets here, it must be 1.5, here must be 0. So there's nothing you can do to it. You cannot change it. But now it's different. There's no battery over here to dictate what voltage should the capacitor be. Okay, there's no 1.5 and 0 positive and negative terminal of the battery to tell you that here must be 1.5, here must be 0. There's no battery anymore. So right now the voltage can change. But voltage can change. But why does it change? Then one will leave it to the next slide to explain why the voltage changed. But for now, we just need to know that the absence of the battery over here causes the voltage to be able to change because it's not locked at this fixed value by the battery. So without battery, you can change. Okay, the battery is there to fix the voltage across the capacitor. So if there's no battery, then you are free to change the voltage across the capacitor. Okay, can change because no battery. Okay, so knowing this, we can sort of make some kind of like prediction. If right now Q is the one that's constant, that means by Q without dielectric is the same as Q with dielectric. and knowing the fact that C is equal to Q over V, and C must increase as you insert a dielectric. Oh, what am I writing? So you should come to a conclusion that V is the one that must change, okay? Because if C is increasing, but Q cannot do anything about it, so V must be changing. So to make the mathematical equal on left and right side, you know that C increase must correspond to V decreases. So if V decreases, that means by comparing V naught without dielectric and V with dielectric, you know that the V with dielectric will be smaller than V without dielectric because it has decreases. Okay, so these are the two different scenarios that might happen if you insert a dielectric into it. Okay, if you insert dielectric, we know that C forever ever, if you insert dielectric, C must increases. Okay, so if C must increase, it must correspond to either Q increase or V decrease. So when does the Q increase? If you have pathway to flow. So if you have pathway to flow, the Q increase. Okay, but if you have no pathway to flow, the Q cannot change. So Q will remain constant. So when will the V decrease? Okay, the V cannot change if you have a battery because it dictates how much the voltage of the capacitor should be. But if there's no battery, then the V is free to change. Then in this case, it will decrease so that the capacitance can increase. Okay, so these are the two scenarios that you can understand for now. So another thing I want to talk about before we go to the idea of how it changed, the voltage, how it changed. Before I go to that, let me just write that if charge capacitor is not connected to power supply, or if it's not connected to anything, there's a term for it actually. Okay, not connected to anything, we call this kind of capacitor as an isolated capacitor. Okay, and say the capacitor is isolated. Okay, so when the capacitor is isolated, that means it's not connected to power supply. Then we know that if we insert a dielectric, what will change is the voltage will change. Okay, so now let's go to talk about why the voltage will change and how will it change. Okay, to do that, I will need to go to a slide that I've made. Okay, so there's no handwritten notes for this part. There's slide for you to explain this. Okay, so let's go through the idea a little bit. Okay, so why does the capacitance increase? Okay, why your capacitance will increase when dielectric is inserted? Okay, of course, this capacitance increase when dielectric is inserted will result in the voltage decrease. But so here, this explanation here will tell you both things: why the capacitance increase and also why the voltage decreases if it's not connected to a power supply. Okay, so let's go through the idea first, and later we'll try to make some kind of summary here. Okay, so the first step is we have a charge capacitor that is not connected to anything. So this one is called an isolated capacitor. We are not connecting it to anything. Okay, so right now we want to insert this piece of dielectric into it. So a dielectric is just any kind of material, but it cannot be conducting, because if it's conducting, then the charge will just flow back down to its original plate. Then you'll be discharged actually. Okay, so we insert any kind of insulator in between, then that insulator will act as a dielectric. Okay, so if you look into the internal structure or the atomic structure, is it called atomic structure? The lattice inside the dielectric, we will see that it's made up of protons, neutrons, and electrons, just like all the other metals in the world. So the protons and neutrons will be stored in this nucleus over here. Then the nucleus is usually at the center of the atom. Okay, surrounding the nucleus, you have your electron cloud, which is negatively charged. So the nucleus is positively charged, but the electron cloud is negatively charged. So this is how we expect the atoms to look like in the dielectric before we insert the dielectric into the capacitor. Now, the dielectric is now inserted into the capacitor. So when you insert the dielectric into the capacitor, due to the presence of this positive plate and this negative plate here, it will cause something called polarization to happen. Okay, so what is polarization? This is how the charge distribution will look like in the dielectric now. So you might notice some differences just right now. You can see that the electrons, the cloud, okay, the cloud has been shifted upwards. Okay, you can see before this, the cloud is balanced, the cloud is well distributed around the nucleus. But right now you can see that the cloud is shifted upwards. You can see there's more electron cloud on the north side of the nucleus compared to the south side. Why does all the electron clouds get shifted upwards? It's because there's a positive plate over here, right? So if it's a positive plate, we know that positive and negative should attract. So this positive plate here will result in the electron cloud being shifted near, want to be near the positive plate. It cannot get away from the nucleus, okay, because it's attached to the nucleus. Okay, you can just pull the electron cloud away from the nucleus. It's attached to the nucleus. But what you can do is influence it so that it's shifted near to the positive plate because of the attraction between positive plate and the electron cloud. Okay, the uniform electric field produced by the two plates push the positive charge in the direction of the field and push the negative charge in the opposite direction. So the positive nucleus over here, they will get attracted to the negative plate. The electron cloud over here will get attracted to the positive plate. So you can see that the positive nucleus will try to shift downward. Actually, I don't think they can really shift, okay? Because the nucleus are usually heavy. You can't really attract them that way. But the idea is one will want to move to the other side. Another one will want to move the other side, okay? The positive nucleus will want to move to the negative plate. The electron cloud will want to move to the positive plate. Whether they move or not, the nucleus, not sure whether it move or not, it depends on the nucleus size maybe. But for the electron cloud, because electron is very light, so you definitely get shifted. But again, they cannot detach from each other because they belong to one single atom. You cannot detach from the electron cloud from the nucleus. Okay, so this process of like charges shifted, even though they belongs in one unit but they shifted apart, this kind of redistribution of charge is called polarization. Okay, they become polarized. You can see one side is polar positive, one side is polar negative. In this case, this upper side here is polar positive, whereas this lower side here is polar. This upper side is polar negative, this lower side here is polar positive. Okay, so right now, the positive nuclei of one row of dielectric molecules are very close to the negative electron clouds of the rows of molecules below it. Okay, I hope you can notice that this is the positive nucleus right now. But this positive nucleus is actually overlapping with the electron cloud of the atoms below it. Okay, this row of atoms, because of the shifting of the electron cloud of the second row over here will overlap with the nucleus of the first row. Okay, so we can therefore think that the charges cancel each other out because negative, positive. So if they stand together at a place, you can sort of assume that they become neutralized already. The positive neutralize the negative neutralize the positive. So because the electron cloud is overlapping with the nucleus over here, they neutralize each other. So you can think of this region to become neutral. So where else become neutral? The positive charge, the positive nucleus over here overlap with the electron cloud with the third row. So you can expect that these will neutralize as well. So the region boxed by this black box over here will become neutral. So you can sort of assume that we can just ignore the charges inside. We can ignore the positive nucleus, we can ignore the electron cloud in this region because we can sort of think of them as being cancelled out or being neutralized already. Okay, so the result of all the constellation in the middle of the dielectric left us with a layer of negative charge at the top of the dielectric surface and a layer of positive charge at the bottom dielectric surface. So we know that this electron cloud of the upper row over here is not being neutralized by any other nucleus. The positive nucleus at the bottom row over here is also not neutralized by any other electron cloud. So they should remain here as being negatively charged on the upper dielectric surface and positively charged at the bottom dielectric surface. Okay, so that's the idea of the effect of polarization to the dielectric material. Okay, so right now the negative and positive charge at the top and bottom surface of the dielectric in turns reduce the electric field between the plates. So as you can see over here, maybe a little bit of zoom in here. Okay, this is the negatively charged upper surface of the dielectric. This is the positively charged lower surface of the dielectric. So if you think about it, positive and negative the presence of positive and negative here, they should result in an electric field, right? So electric field point away from the positive charge towards the negative charge. So you know that inside this dielectric material, there will be some uniform electric field produced due to the polarization. The polarization caused this upper negative layer and the lower positive layer, right? So this upper and lower positive layer will actually produce another electric field, but this time in the opposite direction. Okay, opposite direction to the uniform electric field produced by the capacitor plate. So because of this opposite direction electric field, it sort of weaken the original electric field produced by a capacitor plate. This is the original capacitor plate electric field, but some of the original capacitor plate electric field has been cancelled out by the electric field produced by the dielectric material itself. Okay, again, this upper surface and lower surface here, they are oppositely charged, right? You say this is positive plate, but this is negatively charged upper surface. This is negative plate, this is positively charged lower surface. So you can sort of, okay, there's many ways to think about it. You can sort of think that this is the positive and negative cancelling each other out. Positive, negative cancelling each other out. So the it is sort of like the charge become less charged. The charge never change. The amount of charge stored in the plate never change. But the effect of it is as if it has been reduced. But actually it's just because the dielectric has negative charge to neutralize it. The dielectric has positive charge to neutralize it. I'm not saying that it will come out from the dielectric to merge with the negative charge and neutralize. Okay, I'm just saying that they are standing near each other. Again, it's an insulator, it cannot jump. Okay, but the presence of the positive charge over here will sort of stand in between. It will stand here, right? So it's very near to a negative plate. So you can sort of think of them as being neutralized. So the electric field over here will disappear. So it become weaker. Okay, the electric field in between the positive and negative plate will become weaker. I hope this part can be understood, but if not, you can just read the text over here. The negative and positive charges at the top and bottom surfaces of the dielectric in turn reduce the electric field between the plates. The electric field in between the plates is reduced. Initially, there's a lot of electric field lines, but now there's less electric field lines. Why? It's because of this opposite. It's because of this polarization over here, causing you to have an opposite charge at the dielectric surface, opposite charge at the dielectric surface. So it produces a counter electric field to sort of weaken the original electric field. So the electric field has been reduced between the plates. Again, the charge will never go into the capacitor. It's an insulator, it cannot jump into the capacitor plate. Okay, using delta V is equal to ED, or in your way is usually arranged as E is equal to delta V over D. But right now in chapter 2, delta V will become V, right? Okay, it's just potential difference. We remove the delta, it's just V. So if you know that your E decrease, your D remain constant. So E decrease, it causes V to decrease. So that's why the voltage of across the capacitor will decrease. The voltage across the capacitor will decrease. Okay, then this match with what we discussed earlier. When we don't connect it to a power supply, the voltage will decrease if you insert a dielectric. Why does it decrease? It's because of this dielectric material undergo polarization. So now the potential difference V between the two plates decreases. Okay, so the voltage or the potential difference of the capacitor decreases. However, the amount of charge stored Q at the positive and negative plate remain the same. You can still count them, you can still see the same amount of positive charge on the upper plate, the same amount of negative charge at the lower plate. These two things has not changed. Okay, I'm saying once again, the dielectric will not influence the charge stored in the plate. You cannot jump in to neutralize it. The amount of charge stored in the two plates still remain the same. Okay, the amount of charge stored at the positive and negative plate remain the same since the capacitor is not connected to anything to form a loop. Just now I say it's not connected, so there's no path, right? So there's no path, the charge cannot flow out from one plate to enter another plate, so the charge cannot change. So Q remain constant. If your C increases, the result in your voltage will decrease. So this is the idea why will the voltage decrease when you connect and when you insert the dielectric while it is isolated, not connected to the power supply. Okay, so that explain. Okay, again I come back to this slide. So that explains why if you are not connected to a power supply, your Q cannot change because there's no path, but your V can decrease. Your V will decrease because of the presence of dielectric undergoing polarization to weaken the electric field in between the capacitor plate. Okay, so this video is just to explain this thing on whether the charge will increase or decrease, or the voltage will increase or decrease when you insert the dielectric. So I hope this makes it clear when, in which situation the charge will increase, in which situation the voltage will decrease. Okay, so that wraps up section 1. So next video will probably be on section 2 then. Thank you very much.